Hello, my name is Momin Khan. I am a graduate student in physics here at Wichita State University. I just wanted to take a little bit of time to basically just talk about my research. The title of this research presentation is Convolutional Neural Network in NOVA Vertexing. So I'll kind of just talk about what exactly all this is. So let's go ahead and get into it. All right, so the problem statement, let's just go over what the issue is. Basically, the NOVA experiment is an experiment in physics that looks at neutrino events from the Fermi lab near and far detectors to study various fundamental particles and wanting to learn the nature of these things as well as their interaction with matter. Specifically, we'll be looking at neutrinos. Now, neutrinos are an interesting particle because they are very notoriously evasive. So they don't interact with matter in the normal sense. They're neutrally charged particles, so they're very hard to detect through traditional methods. Usually in these particle detectors, you have a scintillator that kind of shows you the path of a charged particle, and you can do things like manipulate them with magnetic fields and stuff, but you can't really do that with neutrinos. So what we end up having to do is retrace where the neutrino was, figuring out where it interacted with our detector, using a machine algorithm. Now, traditionally, these algorithms have a lot of issues, okay? So you can do things like incorrectly place the vertex, placing it too far forward, too far backwards, depending on what the data set that the algorithm is looking for. So basically, what I decided to do and what I am doing is creating a convolutional neural net, a machine learning algorithm that can kind of analyze this situation much more efficiently with less error. Basically, all you need to do for this thing is just show it a training sample, train it on a certain type of data, and then let it test on that data, and it'll learn as it continuously encounters different situations, encounters the different failure modes, and hopefully get better along the way. So how does this model work? Well, all of the event information is stored in HDF554 file format, and what you're going to do is create these training data sets as well as run it on the machine learning algorithm, and then it'll go from there. It'll go on to the testing phase, and these are the specific definitions that I used, but that's not so important right now. How it works, like I said, go through each of these files, extract the data, the vertex informations, CVN maps, associated energies, things like that, and it'll also split them by data set. So these terms aren't super important right now, but basically just different types of interactions. It'll split them by that and then analyze them separately, and it'll plot all of these events and run the model predictions for each interaction. Then you can kind of take a look at those model predictions, see how accurate it was as compared to our traditional vertexing method, and get some sort of metric there. You can look at both mean RMS values, you can look at the spread of the detector. All of those things I included in this presentation. What I found is that the new algorithm, the machine learning algorithm, was much more efficient. It was much more tightly constricted around zero, around what you would expect. And then also the mean RMS values were much more significantly reasonable. You got much less error and discrepancy. So let me go ahead and show you some of those metrics, explain what these things are. So this is what I call the difference plot. These are basically taking the difference between the reconstruction data, what the or where the algorithm thinks the vertex is located versus where it actually is. That truth information is extracted from the H5 file format, and then you can just plot this. Ideally, you would have everything centered around zero because there would be no discrepancy between those two quantities, but of course that's not the case. So on the left, you have the traditional method. On the right, you have my new neural network, and you can tell just by looking at the numbers, the mean is much closer to zero, RMS much smaller. This range of 3 sigma, which is basically 3 stretches of the RMS, is much smaller. And you can also count the events inside, and I basically did that for each coordinate. Here are some Gaussian fits to those same left traditional method, right new method, and again you can kind of get some idea of how much more accurate this thing is just by looking at those numbers. Like I said, this was done for each coordinate, so if you'd like to look through that, here are the plots for the y and the z. And then lastly, just another cool little metric spread across the detector. So the detector is like a 200 centimeters square basically, and you can look at this plot and tell the true x direction, the model prediction, as well as the reconstruction prediction, you can tell that it is much more tightly constricted to the true information than the RICO was. So you can tell just by not a super huge margin, but definitely it's a work in progress, and it's something that you can look at just to get another idea of how this works. But that is essentially what's going on there. And then in progress, definitely fixing some plotting issues and discrepancies, looking at final state particles, basically the particles after the whole interactions, looking to see at if you're interested in a specific type of particle, how exactly did that prong run, how exactly did that did the algorithm look at that specific type of particle versus others? And then, of course, going forward, going to do much more analysis things with systematically shifted files. And then the plan is to eventually incorporate this into the NOVA experiment. But that is the end of my presentation. Thank you so much, and let me know